Hi there, my name is Amar, and today the topic of my presentation is recurrent all pairs field transformers for optical flow. In this computer vision paper, the Princeton University authors have developed a new end-to-end tunable model for optical flow. Their method beats state-of-the-art architecture across multiple datasets, and it is shown to be way more efficient. And luckily this paper got the best paper award in European Conference in Computer Vision 2020. Here is the list of topics that I am going to cover in today's presentation. Firstly, I will quickly explain what optical flow is. Basically, it is the motion of objects between consecutive frames of a sequence. It calculates the relative motion between the objects and the scene. It does that by using the temporal structure found in a video in addition to the spatial structure found in each frame. So in this picture there are two consecutive frames, frame 1 and frame 2, and time t, and we aim to find the optical flow from frame 1 to frame 2 for a given pixel A with the coordinates x and y. In frame 1, we aim to find the corresponding pixel A prime in frame 2 by predicting the 2D displacement vector dx and dy. Here is a quick demonstration of how optical flow looks. It can give us a natural clue of object trajectories and can therefore be used for object tracking. It is also used in object classification. The only problem with this optical flow is that it is quite slow, and it needs a lot of computational resources. And our paper RAFT helps in both of this problem, and it's providing a way more accurate results compared with the existing state-of-the-art methods. So what is sparse and dense optical flow? Depending upon the application, we can predict a sparse optical flow by selecting a few pixels, edges and corners of an object, or we can predict a dense optical flow by predicting per pixel flow vector of the entire frame. But dense optical flow is more computationally expensive because we predict flow of all pixels. But definitely have more fine-grained features. RAFT mainly focus on dense optical flow. Let's discuss about some related work. As we know that before deep learning techniques, optical flow was treated as an energy minimization problem. But the representation part of deep neural network and the emergence of synthetic dataset, we can treat this as a supervised learning task. The most simple idea is to directly predict flow using encoder-decoder neural network based upon the pair of input images and the properly designed datasets. But the direct output of decoder is sometimes in a low quality, so we usually employ multiple encoder-decoder, and they are stacked to have a course of fine requirement of an optical flow. So observing this, we may directly treat this problem as a relative refinement problem. So in this paper they use subnetworks to iteratively refine and update residual optical flow. So in this picture, the optical flow would be residual between the ground width flow and the current. And so in this picture, the optical flow would be residual between the ground width flow and the current flow, and we concatenate the current flow to the input and iteratively update our flow. This kind of method is limited by the network size. Our model RAFT is also an iterative algorithm, and it uses small modules and can iterate over 100 times on the same amount of computation. So another slide is learning to optimize. The network can be used to predict input parameters of the optimization problem and can be trained end-to-end as long as the optimization process is differentiable. RAFT can be viewed as learning to optimize. It has an iterative update module which resembles steps of a first-order optimization algorithm. Let's see how RAFT works on an optical flow on Ego hands. Here's a video link. Let me play this video to see the actual results. As you may have seen that the results of RAFT is quite good and faster than the state-of-the-art architectures. Let me go further and explain the overview of the RAFT architecture. Here we want to predict the optical flow from frame 1 to frame 2, and RAFT can be described as 3 stages. The first one is feature extraction, second is correlational metric computation, and third one is iterative update operator. Let me quickly explain what feature extraction does. In feature extraction, features are extracted from the input images by using the convolutional network encoders, and in the correlational matrix, where visual similarities between all pair of pixels are computed by constructed a full correlational volume. And the third one is iterative update operator, where it estimates the sequence of flow from F1 to Fn by lookup in the visual similarity matrix and refines the current estimate of the flow. So all stages here in this architecture are differentiable and can be composed into an end-to-end trainable architecture. So let me define how feature extraction works in detail. So far the feature encoder part has stacks of residual blocks. They use separate encoders for context encoding here and visual similarity encoding here. So what about the correlational matrix pyramid? Now after feature extraction, we have our correlational pyramid. It basically has stacks of 4D correlational volume. So let's understand what we mean that 4D correlational volume. So here is an image I1 and I2 as an input image, input frame and g theta as a feature encoder. For feature vector in g theta in image 1, we take the inner product with all feature vectors in g theta image 2 and therefore generate 4D height into width multiple height into width volume. Here we take the 2D slices of full 4D volume. So each pixel in image 1 can produce a 2D response map for the image 2, and after this we apply 2 plus 2 average pooling 3 times to get a full correlational matrix at different stages. So these correlational matrices are the correlational matrix that we want in this process. After the correlational matrix is computed, it is fixed during the rest of the iterative algorithm. The correlational lookup operator, which performs lookup at each time on the correlational volume based on the current estimate of flow. So the correlational lookup key operation. Given the current estimate of optical flow f1 and f2 and the pixel x1 with coordinates u and v in image 1, pixel is drawn in a grid and this grid is a correlational response in image 2. We can express this corresponding pixel in image 2 as x prime as u and v as a flow vector. X prime here. So after we have x prime, we define a local grid around x prime as a grid plus dx, and dx here is a weight integer. X prime plus dx here is a weight integer, and one number of dx should be less than or equal to r. This means that the local grid dx, the local grid should be one number. If we draw it without or equal to 1, so it should be like this. So the local grid is the yellow area. So the local grid is the yellow area around x prime. Here's x prime, and this is the local grid. Also, x prime can be a fraction number sometimes. So the black dots in the local grid, here are the few black dots in the local grid, can be a fraction number. In this case, we need to do bilinear sampling. As we have a correlational matrix shape S cross W into S cross W for all pixel X with the coordinates U and V in image 1 and X prime with the coordinates I and J in the local grid over X prime, we gather this C U V I J. So in the left image, let's say we have a pixel U with the coordinates U and V on the top left in image 1. So we find the correlation response of the pixel in image 2 and then gather the local grid around the X prime. Here's the X prime and this is the local grid based on the estimated flow, and we do this operation for all the pixel in image 1, and at the end we coordinate all these things together, and this is the result of correlational lookup. Later this is sent to the iterative recurrent unit of RAFT. let's come to the iterative update operation. Here as we have the 4D correlational volume. So given is an initial estimate of flow which is initialized as 0, and we want to iteratively refine the flow F1 by correlational lookup and update operator, which is in the black box, which is in the block here, based on the previous estimated flows. So the update block is based on the gated activation unit, and we can understand this mode. We can understand this network as a kind of recurrent neural network. It takes the correlation lookup results as input and hidden features as another input, and takes the context feature as the third input, and it outputs the hidden feature for the next stage, and also outputs delta F for the current flow F. And if we add delta F with F, we have the flow for the next stage. So in this picture, this is a correlational lookup, and the block represents update operator. Here's an update operator, and here's a correlational lookup. So let's define what is the loss function here. For the loss function, RAFT uses L values, that is the distance between the predicted and the ground truth flow over the consequence of F1 to Fn. Here we use gamma is equal to 0.8, while gamma is an exponentially increased in width, and we take n as a 32. So in efficient computation, original computation of correlational matrix is quite expensive, because we are operating on a relative high resolution which is normally unaffordable. Coming to the simple idea, only compute the correlational matrix we need each time during the correlational matrix during the correlational lookup. This gives a complexity of order of k. K is known as the number of iteration. Now I move on to the experiments and evaluation stage. So I will explain how to visualize dense flow. Here we map the direction to the color, and magnitude is mapped to the saturation. For example, in this GIF, if the movement of man direction has changes the colors and saturation depend upon the angle he moves. But if he moves upward, his color changes to green, and when he moves downward, his color changes to red or pink, like that. So in training and evaluation of a data set, they use flying chairs and flying things as a pre-training data set. That is a synthetic data set with 60,000 frames for pre-training of the network, and they use two data sets for testing purpose. The one is Sintel, was a synthetic data set based on 3D images like animations, and 23 training sequence and 12 training testing sequences in Sintel. While in KITTI dataset, they have 200 training scenes and 200 test scenes. So let's move on to the quantitative evaluation. For the quantitative evaluation, they use EPE as an endpoint error, where EP is the the linear distance between the ground truth flow and the predicted flow. Let's move on to the table part here. There are the values in this table. There are values of Sintel and KITTI dataset, where RAFT has a strong generation ability and it outperforms to other methods. And coming to the second red box, contains Sintel test and KITTI dataset and other datasets also, and in which RAFT also outperforms against state-of-the-art architectures. Coming to the qualitative evaluation, on Sintel test sets. So RAFT produce the high quality results, especially at the edges, as compared to the other datasets. Here in RAFT, the bird is seen very clearly, and in other model, like in our model, the bird is seen clearly, and in other model like we see the bird is blur, or we cannot identify what is this. So RAFT also gives best quality outputs on Davis dataset compared with the other methods. So let's move on to the conclusion of this presentation. Optical flow is a very important in computer vision, and RAFT really boosts up the performance of optical flow to another level. This can benefit many related areas. RAFT has a strong generalization ability, which will probably benefit from the learning to optimize pipeline, can shed light on many similar tasks. For the future, work can be done on combining RAFT with different tasks like video restoration and video tracking, or anyone can follow work of RAFT and research on how to design pipeline of an iterative update to let flow estimation coverage faster. That's it from my side. Thank you so much. If you have any questions, please let me know. Thank you.